Thank you. So, very good evening, everyone. It's a hearty welcome to all the participants, respected resource persons, and dignitaries to the day 3 of our AICTE ATAL Faculty Development Program on Intelligent VLSI Design Automation using AI Techniques. We are delighted to continue this journey of learning, collaboration, and innovation with you all. Moving ahead, day 3 promises to be equally enlightening. Today's sessions are designed to practical applications and in industry perspective. We have eminent speakers lined up who will share their expertise and guide us through. Our first session of the day will be delivered by Dr. B. Chandrababu Naik sir. Dr. B. Chandrababu Naik sir is currently serving as an assistant professor in the Department of ECE at NIT Tiruchirappalli since September 2022. He awarded his PhD in image processing from Sri Venkateswara University, Tirupati in 2021. He also completed his MTech in communication systems in 2014 and his BTech in ECE in 2007, both from Sri Venkateswara University, Tirupati. Dr. Nayak's research interests include image processing, VLSI design, and microwave antenna design. He has published research articles in peer-reviewed international journals as well as in national and international conferences. Additionally, he has served as a reviewer for several journals, national and international conferences. He is a member of IEEE and has over 15 years of academic experience across various engineering institutions. Throughout his career, he has held academic leadership roles such as Dean of R&D and Board of Studies member in different engineering colleges. In 2015, he was ratified as an assistant professor by JNTU, Anantapur. He has also qualified in GATE and UGC NET, achieving commendable ranks. He has contributed to GATE training programs as an instructor at several reputed institutions across India. Sir Chandrababu sir, it's our pleasure to welcome you, sir. Thank you for accepting our invitation to present a lecture here, sir. Sir. Hello, sir.
Hello.
Hello, sir. Now it is audible,
Yes,
sir.
yes, it's fine. Thank you. Just I'm sharing my PPT. Few minutes.
Yes, sir. Thank you. Thank you, sir.
It's visible now. Hello.
Visible, sir. Visible,
Visible,
sir.
sir.
Yes.
Chandrababu Naik, sir.
Okay. Okay. Thank you. Okay. Good evening, all of you. It is my pleasure to be part of this FDP ATAL conducting by Sri Rama Engineering College, Department of Electronics and Communication Engineering. Thank you for offering me to this excellent faculty development program. It is today I am going to deliver a lecture on integrating VLSI with Industry 4.0, a new era of smart manufacturing. technology. So these are the outlines. These are the outlines. So design objectives, design challenges, and physical design, steps involved into it, and industry 4.0, and some of the factors and building back blocks of industry 4.0, and some of the comparison between different industries scenarios. Coming to that introduction, first we need to know that what is the integrated circuit. Before integrated circuit, what are the devices we have? A brief introduction need to be discussed over here. So before integrated circuit came into the picture of 1968 as a op-amp developed by Wilder scientist in USA company, Chairfile company in USA. Before that, we have a transistors like BJT and FET and MOSFET and so on. And before BJT, we have a vacuum tube circuits. So these all devices we have for amplification purpose as well as switching purpose. So vacuum tube earlier developed in 1980s, sorry, 1980 centuries and 19th centuries. We have so many drawbacks over there, like power dissipation, power consumption is more, and area is larger, and the cost also very high, and signal to noise ratio is better, less than 1. Because of that, some noisy generated into that instrument, so that we are not going to prolong to use that kind of circuits. There, 1947 and 48, the BJT came into the picture. That bipolar junction of transistor invented by John Borden and Britton and William Shockley. These three scientists invented a BJT that for amplification purpose as well a switching circuit. Even we have faced a lot of problems like a thermal runaway problem we had in BJT, and there is again a power issues like power consumption and power dissipation, and a little bit area occupation is more. Right. There is a three terminal device we know well known, and that cut-in voltages of the BJT. Without cut-in voltage, the transistor never be on, it seems. Right. So without on means, then we can go for the application is off switch of the transistor. If both biasing, both the junctions as on means, it may be act as a saturation region. So one region is forward bias, another region is reverse bias, means we can say that transistor is operating in active region and the application orientation is amplification purpose. So without 0.7 of voltage, the transistor will never be on. So if leads like zero point 0.7 and zero point 0.7 like number of transistor if you are utilized, then the voltages is become as more. Due to that, it leads the power consumption and power dissipation also. So another drawback of BJT is input impedance is hardly, it is, in common collector, it is 1 mega ohm. So when the input impedance is less, then drawing of the current is more, right? There Rin is equal to V in by In. Where In is more, the input impedance become LS. Because of that, again, the power issues will become, that is power dissipation as well, power consumption will come. So these are a drawback we have in BJT. Another drawback that is voltage gain. That voltage gain of common collector, it not even giving 1, right? So it is exactly equal to 0.99. We are facing to get 1 is very difficult in our laboratory. That is biggest drawback. And what is the effect in gain is less means it is giving to effect on stability of the system, right? So we can't get exact output in output side if the gain is lesser. That is another drawback. So what we have to do it for to avoid these all drawbacks, we can go for a FET concept, field effect of transistor, right? So thermal runaway problem does not occur into that FET because FET is a unipolar device, right? The BJT is a bipolar device. Due to that, a majority and minority charge carriers are carry forward. That due to that minority charge carriers or leakage current or reverse saturation current, it leads that a thermal runaway problem, right? So these minority charge carriers current is not there in FET, so we are avoiding the thermal runaway problem, right? And area is less. And another one, the input impedance is ideally hundreds of mega ohm. Little bit it increases. Due to that increment of input impedance, drawing up the current is very less, so that we have saved that somehow power here, right? So power, either power consumption as power dissipation, anyhow. That way we have to manage in FET, right? Another that noisy and all less, and right, cut-in voltage and all, it not factor here. So then we can go for again from JFET to MOSFET technology, right? Of the MOSFET technology, we have, right, input impedance of in 10 to the power of 12 to 10 to the power of 14. It leads like drawing up the current is less, so that we are power consumption, power dissipation, it is less in MOSFET, and the area occupation of area also very less. So thermal runaway problem does not occur into even MOSFET also. So we in 18th century and 19th century, we are making that some, right, application orientation circuit, that is MOSFET. After the MOSFET, right, we are using the integrated circuit, that is the operational amplifier came into the picture in 1968, right? For that, we are using so many applications of amplification and some integration ICs we are designing, right? So in VLSI, uh, uh, come into the picture, then we are MOSFET technology introduced over there, and the number of transistor usage has increased, and occupation of area is very less into the integrated circuit. So device is different, and integrated circuit is different. It integrated circuit is accumulation of all devices and into the part, then we can study a integrated circuit. It is finite. Now, their integrated circuit again different, two different types. One is analog integrated circuit and the digital integrated circuit. So coming to that, perceptiveness of designer and a user, right? The designer always think that perception of the user, how they will buy our product. Let us consider a mobile, right? So mobile, while we are going, right, just we see that as a user, as a cost, how much it is, and how it will be performance, right? What is the functionality rate for this? This only three characteristics we are keeping in mind. We are buying the product like mobile, right? So designer will always think that cost effective as well, power as well, area and technology, right? Nowadays, technology day by day is developing like anything, so that we are using different application over the mobiles, right? So designer always think that what is the cost. So you need to minimize that cost, then only number of usages of more from the customer side, right? So that the designer always think that to design that product with low cost and low power consumption, and occupation of area is very less, and technology should be maximum usage, right? So that difference between a designer and usages of this factor. And this integrated circuit, as I told, this is a different uh, factors that analog and digital integrated circuit. So digital design, again, right, there is a two different kind of thing. One is front end VLSI design, another one is back end VLSI design. So front-end VLSI design, we have again two type. One is system design and RTL design, right? Register transfer level design. These all are coding design. Now coming to the back end of VLSI, we can concentrate on physical design. That physical design means layout design or PNR, right? PNR. These are the design, right? And these VLSI, in that there is a law VA introduced by Morse. So he is a founder of Intel, and he told that one statement that number of usages of number of transistor is doubled for every 2 years, right? And the cost will be goes down. These are the statement today is valid, right? So number of transistor usages in day by day in particular application of design chip. For an example, 8085 microprocessor, we have a 96,000 of transistor, and 8086 microprocessor, we have a more than 1 lakh of transistors. Now you check that any other chip fabrication, the lakhs of transistor we are using into that, right? So then cost wise, it is going to decrease us, right? Then how we are fabricating this transistor in lakhs of level means the reduction of size of the transistor. We are not reducing the entire size of the transistor. We are reducing that gap of source and drain. We are reducing the gap of source and drain. That is a channel length only we are reducing. That by using different technology, we are moving into that. Okay, coming to the Moore's law, still it is valid because of so many factors combined into here. One is a lowest cost and maximum functions, and the area is very small, and speed is maximum and low latency, right? More reliable, right? And it will be also for particular applications. That means it will be market growth maximum, and transistor wise it is the scaling is good, and performance of the battery is good, and some of the investment is fine, right? So these are the factors which we are involved into the Moore's law. He told earlier that all factors are today it is become as reliable, right? Coming to the technology windows. Earlier, we used to take to design that VLSI chip by using some technology that earlier it is that micron technology. After that, submicron technology we use it with a factor of zero point 0.8 micrometer, and later we go for a deep submicron technology, and after that ultra deep submicron technology. Then nanometer technology came into the picture. So we call that 180 nanometer, 90 nanometer. These are the technology. That is a node. Also, we can some people will call node, some people will call technology, right? 180 nanometer, 90 nanometer means there is the size of the transistor. The size of the transistor means the channel width of the transistor. The channel width of the transistor means the source and drain in between. What is the size that delivered is called a technology or a node. It is measured in terms of nanometer. That nanometer, 90 nanometer, 65, 180 nanometer, like that. Now current trend is running with the technology or node is right. 3 nanometer or even 2 nanometer also some of the companies are working on it. So 180 nanometer to 2 nanometer, how it will be the level of shrinking the technology that we need to study very well. That is a more important for a design of VLSI, right? Size, why we are studying this 180 nanometer to 2 nanometer means we are reducing the area over the any application. So we are reducing that a chip area. That is the factor of to mentioning here a nanometer technology. Right. So the process of die size has been reduced over the past node generations. See, 180 nanometer here is generated in the 2000, right? 1998 it started, and after that around 2000 it run with the 180 nanometer technology. Then it 2002 it 90 nanometer technology, and 2005 2010 65 or 45 nanometer technology. Like this a technology will shrinking day by day. That means the channel length or transistor size is reduces a day by day, right? This is now current trend is going on up to 2 nanometer technology. With that, different kind of material we used to use there is here, right? 180 nanometer introduced in the year of 2000. Then there is a material, 6 metal layers has done with MOS technology, right? Copper interconnected technology we have used over there. Then 190 nanometer introduced in 2003 SY substrate, right? In 14 nanometer came into the picture at 2015 FinFET technology they introduced. And now 3 nanometer technology 2021 they are introduced. There is a nano seat FinFET technology and EUV technology they are using. So now running with that technology implementation. So what is the main role of next? What is the main role of VLSI industry? So there are different kind of roles we can, that is one is RTL engineering. He will perform the coding level thing. He used to write in code in Verilog, and that code, whether it is valid or not, there is a testing engineer is there that called DFT engineer, right? Then after that, after the code verification happened, then he has to be convert into a block level or circuit level. So the synthesis engineer need to be do that one. That is called netlist optimization engineer, right? Then after that block level conversion, then he has to be give to that back end engineer, that is called physical design engineer. That physical design engineer is nothing but layout level engineer. So he can do that entire the chip, and after that validate the chip whether it is performing well or not. After that he can go for fabrication and all. These are the main roles in VLSI industry for getting opportunity in the VLSI industry, right? As a faculty, I think those who are interested, you can also try with these, right? Different coding. If you are well known, you can go for RTL engineering, or if you are interested, you can go for testing engineer, or you can go for physical design engineer. Physical design engineer means backend engineer. The payment also very high for this, right? So after my don't mind that here I am discussing my journey after the PhD, right? I worked in engineering college surroundings of Tirupati. Then I started to learn myself this VLSI in physical design backend thing. Then I got the opportunity to work in import chip, right? Import chip company. Their good package they offered. I worked 3 months. Later, I got the opportunity to work in NIT Tiruchirappalli as assistant professor. Right. So you people also concentrate to learn the VLSI. The boom nowadays, the boom for the VLSI is very high. Right. So kind attention. If you are interested, then you can rule that industry also. So my motive in to enter into the VLSI industry is only that package, right? So that package attracted and interested, so that I moved over there. Okay, this is a small thing for my side. Motivation. Okay, and don't mind that management level because because of people maybe migrate to teaching level to like industry level. But those who are interested, you can go ahead also, right? Master maximum people are liking to do some work hardly to working in a VLSI industry because there is a packages, right? Good packages. And coming to the how we can get that, how we can get the job orientation. So why I am discussing this point, required skills and roles of VLSI industry, because you can discuss these things and all with your students also. Okay, your students. So they are final year students or BTech, MTech or PhD. The students you can discuss them to enter into the VLSI core site job opportunities, right? So required skills, what we need to study to get the VLSI job, that means so
Ada apa itu kan pada bawah.
basic electronics subject we need to thorough with that, either EDC and analog circuits, right? And some part of SDLD. These basic knowledge we need to require. And next one is something commands, basic commands need to be learned, that is either Unix or Linux, and some languages should be learned, that is Tcl and Perl, or at least C languages should be learned. So with these skills, you can able to get any job in the VLSI industry.
कैसे
Please,
अरे आज वेला करी
those
भेटले
who
असं अंतवाला का
kindly off your mute mic, some of that disturbance. Okay. So there is a challenges there. There is a challenges for hiring the freshers, right? Even BTech freshers also can get the opportunity. They won't test which college you studied. You studied only that NIT or IIT or a good engineering college or what. They won't test. They test only that what your skills, fundamental concept you have or not. You have skills in basic electronics or not. That everything they will test, right? Those who are strong in fundamentals as well as in languages or technologies, they're definitely they will get that job opportunity in VLSI industry, right? They will see, as you see that brand name of the college, that is shown only that 2 to 5%, right? See, only that depends on your fundamental concept. Mostly 40% or 50% they will check your fundamental knowledge over the subjects. Those who have knowledge in subject, they can rule in VLSI industry like anything, right? It's fact. If you want check with your friends, you check it. They are ruling like anything. Okay. Like that you can motivate your students, and they well known and they will get easily over the company. So how to prepare the resume or resources where we need to apply, where we need to learn that concept in VLSI. There's so many. See, nowadays we should not tell anything. Students known very well. It's using chat GPT, using online resources like YouTube channels or any other resources they can use, right? Everywhere, every concept are delivering very nicely, right? Then they can learn happily and they can get the job. Kindly share this information to your class students, and might be they got opportunity in VLSI industry, means it is very well known for us and very happy for us, right? This is small motive from my side. And what the career roadmap in VLSI industry means, that I earlier discussed, no, digital electronics subjects, what the Boolean concept, number system, and sequential circuits, combination circuit, that registers, right? Flip-flops, that everything, if you are thorough with that, you are master into that. Then basic principle of electronics like engineering, circuits, diodes, BJT, MOSFET technologies, amplifiers, oscillators, these things need to be thorough with that. And semiconductor devices, it's some very large coding, right? You can get it these from NPTEL lecture or any book or any, like any web sources you can consider and you can learn. Along with that, microprocessor, microcontroller should be, and operational amplifier. And the main thing you need to check means that static analysis, timing analysis, STA it is called. Very, very important, static timing analysis. Those who are well known in STA, they are in number one into VLSI industry, right? So what we are doing in timing analysis means always we need to check that setup violation and hold violation, and timing constraint, timing for, and timing violations, and skew or something. Sometimes what are the frequency you are utilizing? These are the factor to learn in STA analysis, right? After that, little bit Perl scripting or TCL scripting if you learn, then you can go for design the VLSI chip. Okay. So these are the main important factors or topics to learn the VLSI industry. If you learn thorough or with that, then automatically the industry is waiting for you as your students also, right? Then where it is a demand. So it has a lot of demand in current scenario in industry wise. Like so many companies are offering, even software companies also nowadays taking the project to design the VLSI chip, right? Especially this HCL, IBM, TCS, Wipro, these also coming competitor for this Intel, IM like IMD, right? And some Qualcomm, Nvidia. These are the companies, the biggest company in India, right? For that, these are the competitors, right? So you ask them to prepare well for getting the job or in VLSI industry, right? And now that what is the spectrum of approaches in VLSI? There is a three category. One is a device level, then you convert into that a circuit level, then you convert into a system level, right? That device level to circuit level to system level. That is a spectrum of VLSI. And this is a flow of uh, uh, that physical design. So entire VLSI flow is this one, right? One is there is a vendor, he is asking that is right system specifications. So one client is there, he has given the project one to the company. So he deliver his specifications. I want this type of the chip. Okay, I have a company. I want to serve this company in different level. So I need a chip like this. So he will discuss his specification and the company architectural design engineer will attend that meeting and he can draw entire the architecture of that specifications, right? Then after the drawing of the architecture, based on the architecture, the functional design engineer and RTL engineer need to write the code, right? Then after writing the code, whether it is code is correct or not, that DFT engineer will be test that code. After the testing the code, whether it is everything is fine, then he will give it to the netlist fellow. That netlist fellow, what he can do, it that code level into a code level into this is called from the code level into that circuit level. This circuit all are AND gate, NAND gate, right? That different kind of gates, right? He can implement from the code level to gate level. That is circuit design engineer. From that, this all gates and circuits need to be keep into some block level. That block level calls macros and standard cells. The small things here looking like standard cell and big blocks looking like the macros. That size of the macro, size of the standard cells given by the netlist, right? This is called the part of a physical design. So above physical design, we have a front-end engineer can do, and after that, that he started the physical design. This is from that it is called a back-end design, right? So there is a physical design having some functionals. There is some subtopic we need to do. That first one is floor planning, right? After that placement, after that power planning, after that clock tree synthesis, then routing. After routing, we need to go for study of STA analysis, then timing and closures, right? Then after completion of physical design, layout done, that we need to go for physical verification. Whether it is all are done correctly or not, we need to go for verification. And then we can go for layout post processing, right? At that time, we have to check that some checks like DRC violations we have, or LVS we have, or ERC violations have, connectivity is there, routing violations, CTS violation, what violations we have, that and all we have to optimize and go for right, optimize and then go for fabrication time. So after the fabrication, we need to check and test whether that fabrication, that chip is working under the stable region or getting and satisfy the all conditions of client what he has given the specification, that and all is satisfied. Then we can package and we can deliver to client. Okay, this is what a flow of ASIC, right? This is the flow of ASIC for the entire VLSI industry, right? So in that, as I here is a high level synthesis means need to write the code. That writing the code, we have to go for logic synthesis, that is in terms of gate level. From that, we need to convert a block level, that is physical design engineer will do. After the physical design engineer, then fabrication and packing will be there. That will be this chip what we are looking nowadays in motherboard, laptops or mobiles. These are the chip is designed by these engineers, right? Only one engineer cannot be do enter the role of VLSI. There is this different kind of engineers we have, as earlier told, that RTL, DFT, right? Synthesis engineer, right? And physical design engineer and verification engineer. This all engineers to be included and design one chip. That chip cost worthy, right? Nowadays in crores of rupee generating, right? This is a flow for VLSI technology, right? Now coming to that background, backend as a physical design. So what is the mean of physical design, right? It is just a process of transforming a netlist into layout. That is design in block level into the layout is called a physical design, right? So in this design, we have to check number of time whether it is a design rule, whatever the we are designing, that rule is correct or not, whether it is connectivity is correct or not, and power analysis is good or not, and timing analysis are well or not. That everything we need to check, and then we go for fabrication, right? Then the main steps in physical design is like floor planning, placement, and clock tree synthesis, as well routing, right? The main intention of this, the main aim of the physical design is there is a three factor, that is one is power, another is performance, as well a area. These three factors we need to consider, and we need to design a chip that is called a demanded chip, right? For an example, if power is very optimized, then it is very helpful for the particular application, and performance is excellent means it is good, and area is very small means it is also fine. Why? Because nowadays there is a mobile industry, right? In Samsung mobile is little bit wider as well as little lengthy as compared to Apple mobile. As you see the difference, Samsung and Oppo Gippo mobile, there is nothing performance levels and power levels as battery levels. It won't be beat with Apple. I think so. It is correct, right? So Apple is ruling like anything. Even today, people are not bothering about the cost. They're bothering about the functionality. They're bothering about the performance. They're bothering about the accuracy. This way the people are running, so that still the Apple cannot be reduces their cost wise, as you observe well, right? This is the main thing to understand in VLSI. So power, performance, area is the factor in entire the VLSI family. Coming to that floor plan, it is the first step of the physical design, right? It is floor plan is nothing but placing the macros inside the area of the block. It's called a floor plan. Placing the macros inside the right core area is called a floor planning. For an example, right, we are constructing one house. In that, we used to go for design engineer, so that will say that I need car parking here, I need bedroom here, I need like dining room here, I need a waiting hall here, like that. We has to be tell to him, then accordingly he can draw one architecture of your house. So if your pakka plan, then only that house may be built, and it will be survived up to a years of years. If that plan is not good, then whatever you had made, that entire will be collapsed within few years, right? So the floor plan is in our design, our home, the basic structure is very important, right? The basic structure is very important. Plan is very important, right? So the same how we are constructing a house or apartment, at the same in our chip also, there is a first step in industry that is called a floor planning. That planning, floor planning should be very well constructed. Then automatically next the designing of chip very easy, and it won't be create much more problem for upcoming designs, right? That is what we need to learn into a floor planning concept. So floor plan should be perfect, then only other structure will be fine. So if you made a bad floor plan, it will leads that die area, wastage of the area, right? So area will be wastage somewhere else, and some congestion will come. Congestion means our words, it is a called noisy or something error you can see. Okay, that way it will be gives. And after these floor plan, we need to check whether it is how much congestion. Congestion means there is a error like that. How much it will be, whether it is good or not, and utilization. Entire the block you as utilized or not, that will be discussed into the floor plan, right? That we need to check. Okay, what are the issues we have observed that we need to optimize, and then we can further we have to move for next step, right? So there is like objective of floor planning. They're minimizing the area and reducing the wire length and maximizing the routability as well, and the shape of the flexible blocks we need to determine. So as you see that here two figures, one is perfectly all blocks made in perfectly with that chip, but another block made, right, little bit space has coming over here, like see this area is wasted here, and this area is wasted here, and this area is wasted here. This is nothing but bad floor planning, and it won't be give good output, and it failure of chip after the fabrication also, right? So we need to design our chip with 100% of utilization, and block sizes should be constant, right? Whatever the whatever way you are designing the block, it does not matter, but the entire area should be utilized with 100%. That is what a floor planning says, right? So for testing these, we have to go for utilization equation that says that how much percentage you have utilized. So macros, that how you can calculate the utilization percentage means there is a formula, that is macro area plus cells area plus blockage area by total area, that will lead that utilization. And what type of block the engineer has given to you, how you can say means there is formula for that, that is called aspect ratio. It is defined as ratio between the width to height. That will lead to aspect ratio. Then aspect ratio should be 1 means the block is nothing but your square block you have to design. Then if aspect ratio is greater than 1, then the given block is horizontal rectilinear block. If less than 1 means it is given the block is vertical rectilinear block, right? These are the things what we need to see particularly in designing of chip. So these all blocks you cannot be done. So people will do along with you, right? So your team manager has given to one block to design or two blocks to design, but rest of the blocks will be another people will do. Okay, like that way. After all blocking and assemble that, then it will become a chip. Okay. Next, what are the checks we need to do for floor planning means how much utilization we need to check, and report design. Whether design is perfect or not, we need to check. And main is keep out margin. KOM means keep out margin. We need to fix. That means macros we need to fix, and we have to create one wall along that macro. Then it should not be overlap with one macro to another macro. That is called keep out margin. Keep out margin should be fixed. Then only the macro cannot be go here and there, right? Then utilization fixed or not, and macros and pins are fixed or not, that and all we have to check into a floor planning, right? Coming to that, as I said earlier, technology is shrinking day by day. See, in 2000 year, there is a technology 180 nanometer. After that, years is year increases, that technology will be shrinking. Now we are running with the 3 nanometer or 2 nanometer, right? So from 180 nanometer to 2 nanometer, we are decreasing the size of the transistor or the area of the transistor. Then so many obligations will come into that. So what are the challenges we are facing while technology is shrinking means one is channel length is reduces. That's what I earlier told. we are not reducing the entire the transistor size. We are reducing only the channel length of the transistor, right? Then coupling capacitance increases. So coupling capacitance value may be increases, right? This also one of the challenge we are facing to shrinking the technology. And size is reduces. And then when the size is reduces, it become more complexity to understand the circuit, right? Then there may be a leakage power impact, more leakage power impact also it will have, and placement issues will have, and color violations we have, and design rule check DRC rules we have. It increases when the technology is decreases, and we have to go for number of times iteration to get a standard output. So we have to go for number of iterations or runtime to get the standard output over the chip. These are the technologies what we are face over the technology is shrinking. Okay. Now current technology challenges in the physical design means current density, power distribution, right? And IR drop. IR drop means power drop, right? And signal integrity. These are the different type of challenges in the physical design what we need to observe. And coming to that, in floor plan, the main concept is this is the chip. So, no, sorry, this is not a chip. This is a block. In this block, as you observe that these are the pin outside of a small things is there. No, this is called a IO pins, right? Input output pins. So everywhere we can't keep these IO pins where we need, right, to one block to another block. How we are connecting, based on that you need to connect a input output pin, right? That is called a IO pins here. And inside of these blocks is nothing but macro. Macro is nothing but, right, macro is nothing but a logic block which consists of all memory things we can store into that logic blocks, right? RAM, ROM, these things and all we can store into a logic block is called a macro. Okay, that macro we need to place along the boundary of this block, right? We should not be keep this all macro. We should not be keep on a middle of the block, right? We should be keep all macros along the boundary. It is the one of the guideline to follow in floor plan. So floor plan itself, it is nothing but placing the macros inside the core area or the block is called a floor planning first guideline. Okay. So some mismatch connection should not be, right. These things and all will be there. Main is then the macro should be placed along the boundary region. It is called. Why we need to place the boundary region means it is easy to connect from input pin to output pin. That connection it is easy, right? So here connection is easy. Here is connection is. Now, if you place that macro in middle of the boundary, middle of the core area, then while connecting from this point to and IO point, so many obligations will be there. Then the routing we have to provide. So there may be crisscross connection and there may be short and open. So at that time we are losing the data or current flow or whatever it is. Then it is a damage of the block, right? So it is violation of that conjunction, right? That's what we should not be keep the these macros into a middle of the region. So these are the some of guidelines we have placing the macros into over there. So this is called, see, this point is nothing but IO pin. These are placing in macros along the boundary region. This I took when I was working into that company. Then I took this one image, right? So screenshot I took. Actually, we this should not be keep in middle of the area, right? This shape is nothing but rectilinear shape, L shape it is. The shape of the block is L shape. My manager has given that L shape here. So this is called shape, and I am placing that macros along the boundary region. This also we can keep on boundary region by using some, some there is a oft small command is that. Based on the command, these all macros should be placed the boundary along the boundary region. Okay. So now a small things white color it is showing. These all are nothing but standard cells. What is the mean of standard cells means? It is called, having all gates, okay, AND gate, NAND gate, buffer, these things and all stored into a standard cells. Standard cells in terms of billion, but macros should be in terms of tens to hundreds only. If you are big block, then you can accumulate that all macros into a with 100 or 200 into particular block, but standard cell should be as maximum as possible. This information given by our team lead only. Okay, that you have to understand over here. So comes to the point as a conjunction. What the mean of conjunction? Conjunction is a required routing resources are more than that available routing resources. Then automatically conjunction will be come into the picture. So conjunction in our language is nothing but error, right? Conjunction means error that defined as so demand over the supply into the routing resources is called the conjunction, or that required routing resources are more than that available routing resources, then also the conjunction into the come into picture. Then where the conjunction will come into the VLSI industry. For an example, if you plan that floor plan badly, then conjunction will be come into over there. If you are not making the keep out margin for a particular macro, then also conjunction will come. If there is a high standard cells placed into a particular area, then also macro will come. One macro, another macro, right? One macro, another macro is overlapped, then also conjunction will come. Like different ways the conjunction will be get. That all you need to optimize and complete the floor plan. Then you can move for next level for placement or power planning. Now, then what are the different kind of conjunction we have? There is a two type of conjunctions we have. One is local conjunction, another one is global conjunction. Local conjunction come only when there is due to over optimization, there is a local conjunction will come. And global conjunction occur when only due to the over utilization, then global conjunction will come. So there are the factor to remove that conjunction. There is methods we have that is called cell padding, partial blockage we need to apply, cell padding we need to apply, and some keep out margin we need to fix, and macro placement modification we can do it, and we can go for a good floor plan. Then like this we can avoid that conjunction also, right? So how the conjunction is there or not, how you can check means this green color all are there is no conjunction. Wherever the spotted is red color, their conjunction is there. Why red color become means there is a maximum that macros or standard cells placed over there. Because of that, there is mismatching or overlapped together. Due to that, the conjunction occur into that place. To avoid that, we need to go for we need to apply the partial blockages or like self adding like that. Okay. For an example, if you see this here, red color is there. Okay. So here, high cell density are placed here. Okay. So it causes the conjunction. To avoid that, we are applying the partial blockages. What code we need to apply means partial blocked percentage is 60%. In that, for an example, over there, 10,000 standard cells are placed earlier. Due to that, that red color came into in this point. So I can understand that there is a conjunction occurred. So what I want to do, I can run with 500 standard cells. Even there is a small dots as a red, then again, like it is causes the conjunction. Then I have to again move into that 250 or 200 standard cells over there. I can keep the, I will apply that partial blockages. In this place, I want to keep only 200 standard cells. Then other standard cells will move away from that. Then there is no red color here. That there is no red color means there is no conjunction happen over there. That's what we need to do in the real industry, right? Then pin density also same. This is called, it is considered as total quantity of pins divided into total instant area of the block, right? At that time, to avoid that pin density, used to add a cell padding or keep out margin. What is the mean of keep out margin means? This is called RAM5 is nothing but it is a stored thing in a block, logic block. It is called a macro. In macro, along the wall, we are creating one side walls, right? Along this macro, we are creating the wall. Our safety wall, while we are constructing our house, safety wall will be there. Total our construction that saves that, right? Some insects should not be enter into our home, right? That's what safety wall we are arranging. And the same way in this block that is called macro, we are arranging that a small keep out margin we are fixing here, so that it should not be away from this place to that place. Then we can avoid the pin density and conjunction, right? So placement blockages we have, there is a three types. One is hard placement blockages and soft placement blockages and partial placement blockages. This is same scenario what I observed earlier, right? Now coming to that power planning. What is the mean of power planning? We need to distribute the power equally in each standard cells and macros. So we are transferring the power from pads or strings. These are the pads and strings. From that, we need to transfer that power to VCC through VDD and VSS. VDD in positive, VSS means negative, right? That is from that it enter into straps. So if from the strap, it enter into rails. So straps contains horizontal and vertical lines, and these rails contain right inside of macro or a standard cells, right? Standard cells contain the logic blocks. Sorry, that AND gate and NOR gate. There need to enter that power. Then only that particular AND gate and NOT gate it will be work, right? Then only we will get the output. Until unless we can't get. So whatever we are transmitting that power, it should be reached to standard cells, or it should reach to our RAM and ROM, whatever it is, right? Then it will be functionality is good, then we'll get the expected output. Until unless we can't get. So I told earlier there is a IR drop, right? That IR drop means power, right? Power if you are not reaching the particular level of standard cell. For an example, I am giving you 5 volts. That 5 volts, actually, we should not give the 5 volts in VLSI. Don't mind. For an example, I am telling. So, or exactly if you want to take, that is, I took in personally in my design, that is 0.188 volts. That much small power I has took to design that VLSI chip, like same that 0.188 volts, if I'm giving to that my block, it should be reach into standard cells. Then only it will give the finite output. Otherwise, it gives that wrong value. Okay. Then uh, uh, like this is a power planning. So there IR drop will be there if you are not reach the power that we need to optimize. And if complete, right, and some power cells are there, special power cells are there. Some these power cells, what will somewhere else area will be empty. At that time we need to throw these power cells, so to complete 100%. That is a special power cells. These are very important to asking that interviewer for us. What is the level shifter will do? What is the retention register will do? These things and all they will ask. After power planning completion, we'll go for placement. So placement means placing the standard cells into the boundary area, core boundary area. That is called placement. Okay. So all standard cells are there in one corner. Just you apply that oft place or place oft, that you apply that one command over the tool, then this all standard cells which we are in a corner region, that will be placed on entire the region of core area. That will be placed on entire the area of core region, core area, right? That is called placement. When it is a placing, it may be happen so many complicated. That means conjunction may be happen, or timing analysis may be happen. That and all we need to optimize, right? So how it will be step by step we'll discuss here. So what are the goal of and goals and objectives of these placement means? To arrange all the logic cells within the flexible blocks on a chip is called the goal. And objective is we need to minimize that critical net delay. Delay we need to minimize. And we need to optimize the power dissipation, right? We need to minimize the crosstalk between two signals, right? And we need to minimize that interconnect conjunction, like different kind of objective we have. So as you see here, right, these all are like, these all blocks are big blocks are nothing but macros, and small blocks are nothing but a standard cells. These standard cells, it will be somewhere else in corner of this region. When we applied that code up to place, then it is releases to everywhere. It places the everywhere into that area, right? But we need to see that standard cell should not be overlap on the macros. It should not be overlap on the IO pins. It should not be overlap one by one. That way we have to consider, and we can, if it is there, then conjunction will be come into the point. Conjunction means error will be shown over there. Like that way, this will be placed. Okay, these are the placing of standard cells into the boundary area. This figure. And the placement is done with a three step. One is global placement, then legalization and detailed placement. What this will tell now? This global placement, it should not be overlap one to other. That global placement has to be said. Legalization. Legalization, we should clear about that. Even there some mismatch to overlap of standard cells and macros that we need to avoid or remove. Right. Then detail placement means we have to use that number of iteration to avoid the overlap in a particular region of the standard cells. That is called detail placement. So these are the three things happen in a placement. So as you discuss, so good placement means this way and bad placement means this way. So bad placement leads that conjunction and it longer wide length from this region to, and this region if you want to connect, it will take long line, right? So in between scritch catch connection comes. Also sometimes short and opens happen because the diversity. So it is avoid. We have to do some correct connection, and we need to minimize that length, right? These things called a good placement, right? So no conjunction in good placement has seen that no conjunction, shorter wire, less metal levels, small delay, low power dissipations. Here, high power dissipation, longer delay, more metal levels, conjunction will be happened, and wire length is also maximum. That causes the bad placement, right? So another important thing is placing macros, placing standard cells into the core area. We have to follow that 5 stages. That right of the code it is that I told earlier. Place underscore up. This is the only one command. If you are utilizing, then the tool will be done everything. Okay, just you put that place off, then it is fine to get all standard cells placed into boundary region. So along with that, we need to follow 5 steps. That is initial core placement, high fan out buffering, initial optimization, final placement, then final optimization. These are the 5 steps to follow placing that a standard cell into a core area. And there is a bounds. So these bounds mean that placing that again, it placing the particular region. So there is a three different kind of bounds we have. One is soft bound, hard bound, exclusive bound. Soft bound means so we are trying to place the all cells into particular area. Hardbound means it is right. It's forcibly we are trying to place the all cells into particular bound region. Exclusive bound means it is like a hard bound only. We are forcibly we need to place a standard cells into particular region. That is discussing as a soft, hard, and exclusive bounds, right? And fourth one is clock tree synthesis. So clock tree synthesis uh, main aim is like to balance the skew, right? To balance the skew. 100% whatever we are transmitting the clock, that clock signal should be reached to each and every standard cell, each and every macro. That is called a clock tree synthesis build. Okay. It is a technique distributing the clock equally among all the sequential element into the design is called a clock tree synthesis, right? The purpose of clock tree synthesis is to reduce a skew and latency. The delay we need to reduce, right? And skew also one type of the delay, latency also one type of the delay that we need to reduce almost, right? And it should be balanced and with 100%. That is called a uh, clock tree synthesis thing. And there is a goal that the clock skew should be balanced and it should be minimize the latency and it reduce the power consumption and reduce that crosstalk. What is the crosstalk? I will discuss later. And reduce the electro migration also. These are the different techniques are there. So we need to avoid, we need to reduce this all problems which we are facing into a clock tree synthesis, right? So before clock tree synthesis, we need to check somehow. The checks are timing estimation is acceptable. So that timing, maybe like what timing it is coming, that time also we need to estimate, and it should be like setup and hold should be meet at a particular time. That is acceptable or not, we need to check. So setup violation, we need to optimize. Hold violation, we need to optimize. That timing estimation is acceptable or not. Whether it come even, then we need to optimize. Whether it is possible or not, that we need to check. Then conjunction is acceptable or not. Yes. Then after that placement completed or not. After the placement only we can go for clock tree synthesis. Why? Because already in floor plan we placed the macros. In placement we placed the all AND gates and NOT gates as a standard cells that we placed into the core area. Then we are inserting the clock tree synthesis. Then we are giving the signals as a clock to each and every standard cells. Then it will be functionality good. Then we'll get the output is finite output, right? Then after that, that if the placement is completed, we can move into CTS, right? Then after the CTS, what are the checks we have? The skew report we have to check. So 100% balanced or not skew, that we need to check. And a clock tree report, whether any latency are there, that we need to check. And power and area, whether it is power, any issues, IR drops are there, we need to check. And area is optimized with that level only area we are constructed or not, that we need to see. And later timing report and setup violation, hold violation, whether it is bad or good, that we need to check, right? So these are the clock tree synthesis. While applying the signal to each and every standard cells, right? Before CTS like this, after the CTS like this. So why we need to apply some buffers means my clock is running before reaching the time, right? Then we have to add, see, the train as one example I'll discuss over here. So in a Tirupati station, there is the Venkatadri train has to be come regularly, right? It is come around 7:30, it seems 7:30 or 6 o'clock. Well, for an example, 6 o'clock. So train has to be come at 6 o'clock, but it came early means what happened is it should be stand over there only, right? Stand over there only. That is halt. We are making 5 minutes came before means, right? It is a violation of earlier train what in the station, right? So it is a violation. So instead to avoid that violation, the train should be stand in front of some stations, right? So for long a station, it should be stand. Why? Because it should not be violate already what the train happened into same the track, right? So we need to make a buffer tree. Delay we have to put, right? So 5 minutes delay. After that, for an example, flat number 1 has to be arrive. Already one train is there in flat number 1. So that entire the train should be it should be stay for long about the station up to 5 minutes. Once this which train as there in flat number 1, if once it is dispatched, then automatically the entire the train has to be reached at the particular same platform. So we need to make the delay. We need to constrain the delay, right? Both way we have to follow. That is called setup and hold violation, right? Before the finite time, it is called the stable means setup. After the finite time, stable means it is a hold. This is called setup and violation thing. And how to implement that clock tree? There is a 4 steps we have. One is clock up, build a clock, route clock, final up. These 4 steps you follow, then clock tree synthesis is completed in your design, right? Next, what is the skew? I am talking about the skew. Skew means it is nothing but differences between capture clock latency to lancer clock latency. That is called a skew. How the skew will come into the picture means because of temperature variation, maybe PLL, or it will come at the voltage variation, right? Voltage 220 volts or 230 volts variation will come, but that variation sudden like voltage variation, it may be causes a skew, and temperature variation, it may be causes a skew, and material imperfection, it may causes the skew, right? And some wire interconnection delay, it may be causes the skew. These are the factor to generate the skew into the CTS. So different kind of skews we have. One by one, local skew, global skew, positive, negative skew, zero skew. See why I kept this all type of the skew means each every interview they will touch this all kind of points, right? What is the zero skew? They will ask. What is the boundary skew you observed in your design? What is the useful skew you observed in your design? How you resolve? This way the questions will come. So kindly attention into that. Then you will be a master into particular technology. Fine. Then in that a clock tree synthesis mainly we used to get a crosstalk, right? And what is the mean of crosstalk? Crosstalk is the signal which that is a disturbance signal due to that coupling capacitance between neighboring signals. It is a crosstalk is a violation that is called a occur due to a coupling capacitance in between a neighboring signals. For an example, we have a aggressive net and victim net. These two type of net we have signals. Because of these, it violated the crosstalk. How it will be violated the crosstalk? Let me check. So crosstalk has divided two type. One is crosstalk noise. Another one is crosstalk delay. So crosstalk noise is occurred only when the aggressive net is switching and victim net is a constant. Let us assume aggressive net is switching and victim net is constant. When victim net is constant, aggressive net is playing and keeping some spikes on the aggressive net. It is occurred due to only when the due to coupling capacitance. Due to the coupling capacitance, some spikes are coming into the victim net. This is called it causes that a noise. It causes that a glitch that is called crosstalk noise or crosstalk glitch. Because of this effect, it functional failure happened into our design. Next, coming to the crosstalk delay. So aggressive net and victim net both are switching, but victim net is gets a delay due to the coupling capacitance. Then we'll get the crosstalk delay. Okay, because of the delay, it will become crosstalk delay. So because of that, there is a setup and hold violations occur. Okay, so these are the different kind of crosstalk we have. It should be optimized. Then only our design will be fine. Next, there is a positive crosstalk and negative crosstalk, right? There is a positive crosstalk means aggressive net and victim net both are switching in opposite direction. Positive crosstalk occur only. Hello,
Huh?
positive from the
120.
Can
admin.
you please mute that?
From
Mute the
admin, you can
microphone.
take care of that. Okay, fine. Thank you. Positive crack. So aggressive net and the victim net both are switching opposite direction. It leads the positive crack, right? And it's good for hold violation, but it bad for the setup violation. And coming to the negative crosstalk, it occur only when both nets are in switching in same direction. Then negative crosstalk will be occurred. It is good for setup violation, but it is bad for hold violations. These are different crosstalks we have. We need to optimize this. And the last step for the physical design is routing. So routing means to establish the connection over entire the blocks or gates or anything, right? This is called routing. So physical connection between a signal pins into the metal layer is called a routing. So various standard cells we have, that every standard cells we need to connect. We need to create the path that is called routing, right? Now there is a two steps over the routing. One is global routing, another one is detailed routing. So global routing is determine the local of all interconnects, and the objective of this is nothing but minimize the total interconnect the area. Right. And coming to that detailed routing, as you see that figures, detailed routing and global routing, how it will be. I think you're clear about it. So the detailed routing is having the completely route in all interconnection over the chip. This is called discussing the detailed routing. And the objective of detailed routing is we need to minimize that total length, interconnected length we need to minimize. Then it is shows that detailed routing. Okay. So there is objective 100% connectivity for every system. The system means every standard cells or macro we need to connect the path. Then only it reaches the signals or power. It will be reaches to entire standard cell, enter the macro and functional good. There is a no crisscross connection. There is a no SAT and open happen. If it is the SAT and open happen, then it is functional. It is a failure of functionals, and the power cannot be distributed over the standard cells. Then it is a failure of chip, right? So these things and all we need to consider, and entire the chip we have to create the path to transfer that our signal and power to over there. Okay, so 100% connectivity of the system. One is the main objective of the routing. Another one is we need to minimize the area, and also we need to minimize the length of the area. Okay, these are the things we have to follow for routing, and there are the constraint we need to see. Number of routing layer, how many layers are there in that routing, and what is the design rules we have followed over that, and what are the timing analysis we have done, and whatever the crosstalk, whatever the process and variation, that and all we need to see in routing constraint, right? There's a flow of routing, right? I told earlier there is a global routing. That global routing intention is to minimize the total interconnect length, right? And running time also we need to minimize. And there is a two steps in global routing. One is initial routing, another one is rerouting. So entire routing flow we have categorized as four. One is global routing, another one is track assignment, another one is detail routing, another one is search and repair routing, right? So global routing, in that the main intention of global routing is to minimize the total interconnect length. And also we have to minimize that runtime. And there is a two-step performing the global routing is initial routing, rerouting. What is the mean of initial routing means? We need to see the shortest path of the design. So we are connecting, we are creating the path from one end to another end. In that, how the way we are creating the path, whether it's the longest path we are creating or the shortest path we are creating, that is the matter over there. If you take the longest path, there's so many obligations will come into, so many constraints will come into the factor. But you need to see always the shortest path. For an example, if we are running with our home, we see always shortest path over the vehicle, right? We don't want to go for longest path. We have to go, we select only the shortest route. Then we can reach within a few minutes to our home, right? That's way we have to create here also, right? That is called initial routing. And rerouting means if any affected area, for an example, road construction will be there, then we have to take another route and we'll have to go. That is rerouting. Rerouting which all affected area we have to check and we have to reroute again. Then second factor is track assignment. This track assignment says that whatever we had created the path that will track same or not. For an example, we ordered that like what we call in a Amazon and something product we are ordered, that we are tracking that where is shipyard has done or not, where the product still now, that we are tracking. Same way we need to track our input to insights of that particular block. That is called a track assignment. And detail routing. Detail routing also called a real routing. Here the main purpose of detail routing is nothing but to reduce the number of vias, right? Vias means crisscross connection, 1 into 2, right? Like that. So with that, we used to take DRC violation. We used to measure that DRC violation and we need to check the timing violations, everything. And then last step is steps search and repairs. So in this, we have to check whether shorts and open happen into that connection. If it is shorts or open happen, then again we have to do that in like reroute. Then we have to transmit the our signal or clock. That will do by just writing that set DRC, that automatically all commands with that command we can do that repairs into over the damage area, right? This is called routing flow. And up to this the physical design happened. So this floor plan, power plan, placement, clock tree synthesis, and the routing. These 5 steps are done into that physical design. So in these, right, just you had enter a just command. With that command, we are getting every steps, right? You are not doing anything. Everything done by the tool only. In that tool, you are just applying the command. Based on the command, all macros and placements are, sorry, macros and standards are placed over the area, and we are connecting the power. We are connecting the clock signal into over there, and we are creating the path over there. Everything we are doing with just the command, whether it is after place after or set DRC, some commands we used to do. Then 60% we are with command we are done. This all things done by only a tool only. Okay. So, but rest of the 30 to 40%, sometimes we are not able to minimize that latency. We are not able to minimize that timing violations, conjunctions. Then manually we have to try to optimize these all errors. So violations as well as conjunctions. That is called manual issues. So manually we have to optimize that error. That what type of fixes we have to do in manual into our PNR stage. That is called a manual issues. Right. Engineering change order is called issues. Right. We have to fix. For an example, there is a IR drops. Already we had done some code that IR drop we optimize. Still we didn't optimize properly. So then manually we have to enter over there, and we have to do that where IR drops are coming, what is the reason it came, that we need to check, and we have to apply that manual scenarios. Then we can optimize the IR drops. There is the antenna violations, manually we can optimize, and electromigration, that also we need to optimize, and crosstalk we need to optimize and fixes, maximum transition, maximum capacitance, and setup and hold violations also we need to manually, sometimes we need to optimize. So with this 100% optimization, then we'll get the correct chip. Okay, so it will work stable, so that it will be this fabricated. After that it goes to region of what we call client people. Okay, so once the layout is finished, then we can verify if it is coming proper output, then we go for fabrication. After the fabrication, we'll go for packaging. Before packaging, we have to go for again check. Okay, then it is finite work. Then we can send to a client people. Right. This is the way how we are designing a VLSI chip over the industry. Just you keep on mind. This is what we need to discuss. Okay. Then coming to the point, what is the industry 4.0, right? This is the word organized by Germany, industry 4.0. It's referred new area of organizing factors. It is also called a smart factories, right? And it focus on greater flexibility in production. And the aim of this one is it is a resource optimization. Okay, then it helps the better customer services. So industry 4.0 is helps that a better customer services, right? Now, coming to that, a principle of factory 4.0 or industry 4.0 is classified in three different way. One is digital and flexible factories, and the second one is right. Second one is and simulation and data processing, and the fourth one is efficient use of energy and resources. Coming to the digital and the flexible factories is like manufacturing processes become more adaptive, and it's digitally controlled, right? This manufacturing process is becoming a more adaptive, and it controlled by digitally, right? Now coming to simulation and data processing, the use of powerful tool and real-time data analysis for decision making, that is called simulation and data processing. And efficient use of energy and resources means that a smart management to reduce the wastage as well as improve the sustainability. This is called efficient use of energy and resources. Okay. Now there is a industry. See, actually, now updated is industry 5.0. In our thing is that industry 4.0, but updated one is Industry 5.0. Now, one by one, I will tell you. Right now, Industry 1.0, it came into 1970, sorry, 1780s. Right, it is just a missionary. It is just a missionary. It's done in industrial production based on the machine powered by water and steam. Right. So this machinery will work by water and steam in 1780s. This is called revolution of industry 1.0. 1.0. Okay. So then after 120 years, then second generation came. Okay. That second generation is nothing but industry 2.0. It came into 19th century, right? It is electricity based one. So mass production using assembly lines, that electric based thing it came, right? Now after that, 3.0, the industry 3.0, it is came into 1970. This is a computer-based technology come into the picture. All are automation using electronics and computers, and it will do for digitalization and interconnect. Sorry, internet. Everything will come into the third industrial revolution, right? And it automation of production throughout the electronic and IT systems, right? This is called 3.0 for industry. And coming to that industry 4.0, it is a internet based one, right? It is internet based one. It like AI and robotics, IoTs, blockchain, and crypto. These all technologies came into fourth industrial revolution, right? So that is called today's digitalization we are doing, right? So artificial intelligence nowadays is running like anything. AI is ruling like anything in the industry and entire the world, as you well known in this factor, right? And robotics, right? And the reality, virtual realities, right? Augmented realities. These all are factors of industry 4.0, right? So after industry 4.0, right? It came that revolution of industry 5.0 also. That is future personalization, right? Just introduced in 2020, right? That 5.0 of industry is equal global and trade potential. Based on that, that innovation purpose and inclusivity, it come into fifth industry generation. Okay, so it consists of deep multi-level cooperation between people and machines, right? It work with multi-level cooperation of industry as well as people. That industry means mission and people. So collaborated with that, and it will be run behind the artificial intelligence. That's what in coming into fifth industrial revolution. Okay, this is the revolution of 4 point industry 1 2 up to 5.0, right? And industry 5.0, it consists of cloud computing, additional manufacturing, sorry, additive manufacturing, and cyber security, right? Automation, robotics, drones, right? And IoTs and horizontal and vertical system interaction, sorry, integration, and augmented realities, simulation wise, big data and analytics. This all are comes into industry 4.0 and 5.0 both, right? So nowadays these technologies are ruling like anything in industry, right? IoT is main and AI is main, right? Then future of industry 5.0, right? You as you see that opportunities where we can do it and what are the limitation we have, what are the futures research we have. It is completely for research people, those who are doing into a communication background or anything, right? So coming to that uh, opportunities, right? There is a and medical things we can go ahead. So in medical things, many changes will come in future of industry 5.0. Okay, so smart infrastructure we can expect, and clean energy we can expect, and intelligent transportation we can expect, and a smart clothing also we can expect into future of industry 5.0. These are the opportunities we have. And coming to the limitations. So limitations is very important task while security issues, that information security, whether our data, how much it will be secure in our internet, we don't know. That is fact nowadays, right? So you are speaking XYZ being over the mobile, somebody listening also, we don't know. Your bank balance, somebody like they can visualize and they can theft also. See, nowadays, digital transaction is failure, so many factors, because of so many factors, right? So these are the technology as uh, there, but usage of technology is wrongly, then this all kind of impact is coming to pictures. So be careful with this, right? So adjustability and human machine collaborations will come into that limitation, and digital forensics will be mismatched, and high skilled workers also. See, now robotics will come and AI will come. As you well known that because of these AI and the number of job opportunities are we are losing, like that news are coming into day by day. That how much it will be, we don't know, in fact, but the news is like same, right? So this we have to consider in the limitation wise. And future research, this more future research is going on, as you well known as a blockchain, quantum computing, right? This AI, right? And also security and trust areas, right? These are the future research. Those who are still need didn't start that research over, now you can start that blockchain area, AI, that security and trust areas, and intelligent networking areas, right? And quantum computer. You can start that new area so that you can get the good publication over there. These are no future of industries 5.0. And path of the communication, this is just like what I earlier discussed. There is a different way to industry make why smart system, that smart engineering. It is divided in cyber physical system and cloud computing. It is based on IoT. That IoT comes in a consumer as well as industrial IoT. Then industrial IoT again is divided in many factors like mobile devices, right? And location detection technology, IoT platform, and human vision interfaces, and big data analysis, augmented realities. This all are comes into the factor of industrial IoT, and it is ahead of that. And also it make as smart sensors and 3D printing as well, this mission automation. This all technologies will implemented in IoTs, right? By the IoTs. And there is some characteristics of industry 4.0 and 5.0. Is main thing is interconnectivity, that is IoT and cyber physical connectivity. There is a machine devices, sensors, and people are connected throughout the IoT, right? And also real-time communication between physical equipment and digital system, there is enabled for smart factories. This is a interconnectivity with IoT as well as cyber physical things. And next, big data and analytics. This is a massive amount of data are collected from various production lines, machines, and supply chains, right? We can collect this massive data from you there, and we do analytics over there. Big data analytics is used for find the patterns as well, a optimization process, and it makes that a faster and evidence of the based decision. This is a data driven and a decision making for the big data and analytics. And coming to that other characteristics, automation and smart machines. Some of the factories are uses AI powered robotics, automated systems, and self learning machines. These machines can diagnose and self-correct and self-optimized without waiting for human input. These are automation and smart machines, right? Another characteristics of Industry 4.0. And simulation and digital twins. So it predict failures and testing the changes virtually, and it reduces that downtime, right? And processing time. Are you getting? Then digital models of real system. It's allow the companies to simulate the production production process. This is a simulation time. And coming to that cloud computing, that cloud platform is store and process the data and also making it accessible from the anywhere. Right. We are from the any location, remote location, you are accessing your data. That is called cloud computing nowadays. Right. It allows the scalability, flexibility, and also that cost efficiency in factory operations. Right. And another point of the characteristics in 4.0 is security, cyber security. With more connectivity and security become critical. In nowadays, right, it will be very critical to save the or to secure our data or anything in personal, right? So industry 4.0 is ensure that data integrity, confidentiality, and protection from the cyber threats. These all are cyber security. This all are comes into cyber security, right? And coming to that, automation systems. These production systems are increasingly self-configuration, as well self-maintenance, as well self-organization. That it reduces that dependency on human supervision and improves that efficiency and reliability. That called a autonomous systems, right? Another characteristics is human machine collaboration, that workers collaborate with the smart machines like robotic and AI, right? We are collaborated with smart machines like robotic and AI, and use of augmented reality AR and virtual reality VR and wearable devices, which improves that training and guidance and productivity. These are the human machine collaboration which we are doing now. And one more characteristics for the industry 4.0 is sustainability as well as resource efficiency. That this industry focus on energy efficiency, waste reduction, and optimal use of resources. The small factories contribute to green manufacturing and lower environmental factors. These are a characteristics of a industry 4.0. Right. And uh, coming to okay, coming to comparison of today's factory and industry 4.0, we have a total differences. So today's factories are mainly reactive. They didn't and respond. Sorry, they detect and respond that problem after they occurs, right? But industry 4.0 factories are proactive and autonomous, right? They predict, prevent, and optimize the operational continuously, right? Today's factories are reactive one, but industry 5.0 or 4.0 are proactive and autonomous, that already protected and prevent and optimize that operation of continuously. Then uh, it shift from human dependent monitoring to that a machine intelligence and automation, right? Then this transition enables that higher efficiency and reduction downtime and lower cost, as well as the better resources utilization. These are the comparison over a today's factory as well as a 4.0, sorry, industry 4.0, right? So, and I can conclude with these points. So I think I covered this all points which suitable for my title. I hope it's clear for you all. Kindly, any queries, let me know.
Any questions, participants?
No questions, sir. You should be asked some questions. I think most probably surrounded Tirupati region faculties only attended, right? So you can speak very well. No issue.
Actually, we have pan India participants, sir.
Madam, hello.
Actually, we have pan India participants, sir.
Okay. Okay, then.
Okay, sir. Thank you, sir, for highly informative and engaging session. The participants truly gained valuable insights, sir. Thank you so much, sir.
Okay, thank you for all. Can I leave?
Yes, sir. Thank you.
Yeah, if you have any doubt, please rise and you can search my mail ID in website in NIT Tiruchirappalli, Department of Electronics and Communication Engineering. Over there, my mail ID is there, the chandrababu at the rate of nitt.edu, and you can always acceptable to send me any request or any information regarding VLSI or what else, right? So I take opportunity here and thank you for all.
Thank you, sir. Thank you. Moving forward, next we have session 2 by Mr. V.R. Pradeep Bharadwaj, sir. Mr. V.R. Pradeep Bharadwaj, sir, has 14 plus years of experience in VLSI design and DFT implementation. He currently leads the product engineering team at Synopsys India Private Limited for the DFT implementation tools. Previously, he worked at Intel for over a decade, focusing on DFT implementation, CAD flow development, and managing multi-domain dependencies in DFT. He holds a bachelor degree from Sri Vidyaniketan Engineering College and masters in VLSI design from VIT University, Velu. Sir, a hearty welcome, sir.
Hey, thank you, ma'am. I hope you all can hear me.
Yes, sir.
Perfect, perfect. I mean, thanks for inviting me. Hopefully, I'll be able to provide some insights into what are the latest trends in DFT in terms of artificial intelligence, right? So particularly AI is now the buzzword you get to hear everywhere. So hopefully I'll be able to give you some introduction into what kind of AI things that we are looking for within the DFT, and some of these are already in production grade quality, right? So thanks for the invitation.
Yes, sir. Pleasure is ours.
So we can get started, or do we need to wait for a few more minutes now?
We can start, sir.
We can start? Okay.
Yes, sir.
Sure. So I might need help. Just let me know once you can see my desktop, and then after that I will take it forward.
Yes, sir. Yes, sir. It is visible.
Okay. Thank you, ma'am.
Thank you.
So
Thank you.
I have prepared a very compact slide deck because I don't want to kind of, especially this is like the dinner time. I don't want to bore you guys with like lots and lots of theoretical data, but I want to kind of like kind of the key takeaway that you would get at the end of the presentation is to give you an exposure to what kind of technology developments are happening in terms of with AI assistance in the DFT design for test, and why we need them, and then what is the future holding for us in this entire AI-driven space. Okay, so now, so before we get into the like different technological advancements of like DFT with AI, right? I mean, the basic question that I think everyone would have is, okay, I mean, why AI? I mean, is it really needed? I mean, what is it helping us? Or it just a trend that we are going ahead, right? So if you look at it in a general term, not just in VLSI, right? So AI is particularly helpful when you have high volume of data. Like for example, we even call it as like a data tsunami, right? I mean, especially if you take VLSI, so there are so many things, right? I have my microarchitecture, I have my floor planning, and then I think just before this, I think Chandrababu sir was also talking about the overall design flow, right? I mean, every aspect we need to make a decision. What kind of recipe I need to use? Okay, what's going to be my yield process node? What's it going to look like? Which manufacturing technology? How is my power delivery network? So if you see, right, like when there's so much of data available, now can I take this data and get something meaningful out of it? I think that's where AI is going to really help, right? I mean, it's going to really help us to take this data that is available in front of us and then help with kind of simplifying the complex decision making process that is involved. Like if you look at a traditional VLSI design, right? I mean, we need to look at like, okay, what is gonna be my microarchitecture? What is gonna be my packaging? Will I have a monolithic big die, or I'm gonna go with chiplet based small dies integrated into a package, right? I mean, what is gonna be my strategy for packaging, power delivery, whatnot, right? And then, okay, looking at my technology, if I go for higher speed, how does that impact my yield? Or do I need to improve the yield? Like how much compromise do I need to make on the clock speed? So if you see, right, so these are the set of decisions that are interconnected when you start a chip design phase, right? And then this is where AI is going to help us to take this volume of historical data that every company has in terms of manufacturing the chips and see if it can help identify the patterns, subtle patterns that the humans are very difficult to spot. Like, for example, if you look at, like, I mean, like if you see AI, right? AI is not logical. See, AI, what it does is it takes a lot of the data that you throw at it, it's going to chunk at it, and then it's going to go look for some visible patterns to make some conclusive analysis out of it, right? So this is where this volume of data is going to help in kind of narrowing down on what kind of decision we are taking. And then why is it needed? So if you see, right, so right now in the industry outside, there is like a heavy competition. Like every domain, every tool you take, or every manufacturing you take, there is a competition out there. And then the requirements keep changing in few years, right? Let's say you miss a window for your chip in by 6 months, maybe you are going behind for a long time and your competitor would catch up, right? So the time to market is very key. I mean, just to give an example, right? I mean, traditionally, if you look about like at least 6, 7 years back or about a decade back, right? So a traditional server CPU design, if you look at it, right? I mean, it would take somewhere between 3.5 to 4.5 years, starting from an architectural decision to a tape out, where we actually send it for the manufacturing. Like 4 years is a good amount of time. But now in the current market, 4 years is like a game-changing duration. Like I don't think we can afford to do it anymore now. So now we are looking at a design, a complex design to be out there in less than 2 years to catch up with the market requirements, ever-changing requirements in the market, right? So now, how am I gonna achieve the work that I was doing in 4 years traditionally in less than 2 years, right? I mean, that's where we are relying on AI, right? So today, I'm not looking at, we should not look at AI like as a competing environment. AI is more like augmenting the efficiency that you would generally not get. So today, people, the way how industries are using is more like an augmentation. It's not like AI is going to fully replace the humans, right? So at the end of the day, the power of AI is to optimize some of this decision making, which would take a longer duration for us, and then we focus on something that is really efficient, right? So, like, if these requirements are like, if these are the things in your environment, I mean, that definitely we can rely on AI to basically go ahead and then improve the efficiency in a way. So now, like, kind of moving ahead, right? I mean, if I take the concept of AI and look at it today in a VLSI design, where all does it fit into? I mean, pretty much if you see, right, starting from architecture till reliability, AI has like one or the other purpose where it can improve the efficiency. Let's say we start with an architectural planning. Now, basically, maybe I need to come up with a micro arc. I need to see micro architecture and then see like, okay, what are going to be my power, performance, and area trade-offs? Can I use my historical design data and micro architecture and see, can AI help me in coming up with like a preliminary set of architectural requirement, right? And the next phase after the architectural planning is like we go and do build our IPs and RTLs based on the specification that we receive for the particular chip that we are designing. So there, I mean, one of the cool things that I have also personally used is that generative AI which is helping in the code generation and RTL generation, right? I mean, just to give an example, the other day, so I was helping our R&D to create a small test case, unit test case, and they were like, "Hey, Pradeep, can you take the small test case and I need like maybe 20 such instantiated block, and then maybe I want different reset signals going into the set of signals, right?" So what I took is I took the simple unit test case that I have, and then I modified it to an extent where I gave like basic syntax, like, okay, add these resets, and this is how I instantiate. Now I asked the Copilot, hey, can you help me complete this to generate a test case where I have 20 instances of this IP with different reset configuration. And to my surprise, the first attempt, the RTL that it actually generated is pretty much accurate. So if you see, right, I mean, with enough context, right, that's where the Copilot is helping us. Now that did not kind of take away my job, right? So what it helped me is instead of me spending 2 hours building a test case, which is not my real job, but my real job is basically like to do a unit validation on the new enhancement that R&D was doing. So what I did is like I was relying on Copilot to generate that RTL. Now I focused to kind of spend the rest of the time in improving the design spec, functional spec, and giving feedback to R&D, right? So today that's where the generative AI is helping, not just the software code, but even the RTL level, right? So it can generate. And same thing when you go to your implementation phase where you are doing synthesis and PNR. So this is where the RTL gets translated into a logical design and to into physical design, right? So here, if you see, right, I mean, if I take any design, like I mean, a traditional chip can have hundreds of blocks. Now, hundreds of blocks, each block, depending upon its criteria, might need different fine-tuning recipes. Like somewhere, maybe I want to improve for power. Somewhere I want to target for area, or somewhere maybe I need to improve the congestion depending upon the block, right? Now all these manual work, so it can be achieved using an ML guided optimization for timing, congestion, power, whatnot, right? So this is where the machine learning is gonna actually help us. And same thing with DFT and ATPG. So we will go into some of the practical applications that we are solving today with AI. So same thing like for DFT and ATPG, we are relying on AI to actually help us improve the fault modeling, to improve the test pattern generation, get some higher coverage, and not spend like a lot of time in terms of improving my pattern that will kind of work out of box in my post silicon, right? And for the verification, like the similarly to the way how uh, Copilot or any other AI that can generate a code, it can also come up with test benches, and it can also kind of identify some abnormal scenarios in your design and then maybe create a test bench for that one, right? So, and the last one is for the yield and reliability. Okay, now as we go into technology, you will keep hearing, okay, it's like right now TSMC is manufacturing in 5 nanometer, 3 nanometer, and whatnot, right? So as we go into this advanced process node, the biggest challenge that we have is yield. Like yield is like if I manufacture, let's say 100 chips, out of that 100 in a wafer, how much are really working? So that directly impacts my cost, right? So what there are a lot of work happening on, can I look at the layout? Can I look at the failures? And can I draw some correlation from a manufacturing to layout to, okay, what can improve my yield? I mean, what is causing the chip to fail, right? I mean, there are like some work happening around that as well, right? So that if you see, right, I mean, end to end, definitely AI is actually playing a role in improving the overall productivity and also kind of optimizing my time to market and optimizing the design in a way. Now, at the end of the day, right, see, like now kind of doing a deep dive into DFT, right? So at the end of the day, what is important for DFT or any chip is what is my DPPM? So any manufacturing at a high level, any company, right? They don't talk about my coverage, pattern count, at a high level. At a high level, what matters is what is my total test time and what is my DPPM, defective parts per million. So that these are the two key important things that people look at a high level. The reason why we look at it is like if you look at it traditionally in any company, if you see, right, they will say like we are shipping million parts. Now let's say each chip, even if it takes like about like 2 second, 5 second, right? And what we are looking at is about like 5 million seconds of testing. If each chip for me to test take 5 seconds and I'm shipping a million part, I'm spending like 5 million seconds on the testing, and which is like close to what, like 2 months, if you see, right? So, and the test times, every company, when they do tests, they pay for the manufacturing entities like TSMC, Intel, or Samsung, right? So there are different foundries, right? So foundries are for like are the companies who have this ATE test equipment, right? They pay for it. The reason for that is like every test equipment costs like millions of dollars. So not every company can afford to buy it and keep it, right? So what they do is like they kind of use this existing available manufacturing and other offshore vendors to kind of do this testing, right? Now that is a costly effort. So that's why the test time I need to reduce so that the amount of time that I'm spending validating the chip and then the amount of cost that I'm paying, that's gonna come down. And the other key thing from a chip is that like whatever is a issue or a bug, it need to be caught during my ATE wafer level testing, or it need to be caught during my functional testing, or it need to be caught in my vendor testing. It cannot go into my actual consumer end. So the reason for that is like, especially if you take autonomous driving or auto or healthcare, right? The mistakes are going to be very costly. So if you look at like a traditional server, so what we are looking at is like maybe we are looking at like uh, defective parts to be in hundreds. But in kind of autonomous or general healthcare kind of a chips, right? The defective part per million requirement as per the ASIL standard is like almost like it needs to be less than 10. So that's the level of kind of confidence that we have that we should have when we send out, right? So yeah, so at the end of the day, to achieve these overall two high level goals, which is my time to market and my reducing my defective parts per million, which is basically improving my coverage. So we are looking at AI to kind of optimize these things. Right now, as I mentioned, uh, so some of these are not the theoretical ones that I'm presenting, right? So today we do have solutions which are like production grade tools that are available from like kind of major EDA vendors that people have been using in terms of early pilot, or they even have some chips that have kind of went out using these AI like kind of space optimized solution basically. So like some of the vendors which are out there, basically Synopsys. So the platform, the TestMax platform has an ML-driven fault modeling. Similarly, Cadence, which Cadence has a Modus DFT. So they also have AI-assisted pattern generation, and then they also have like X masking, X bounding with a predictive fault coverage. Like especially my X sources affects my like kind of my logic based validation that happens. So it's important to make sure that like we kind of mask the excess, right? And then similarly, Siemens, which is well known for the test today, right? So from an NDA vendor point of view, like they have multiple extensions that kind of does an ML based diagnostics, and then can you take a look at the failure that has happened and then translate into, okay, what could have actually caused it? Can you come to a root cause? And can you take this information and then see how to improve the yield, right? So these are some of the existing solutions that are out there from these major EDA vendors. Okay. Now, kind of going into a deep dive further into some of the, like I have identified three use case scenarios where basically the AI is helping the DFT in kind of like improving the overall efficiency and solution. So let's go over them one by one. Okay, so the first one that I wanted to cover is the AI assisted ATPG. So now, if you see any traditional pattern generation that is out there, so the biggest challenge that we have is engineers spending like tons of hours to fine tune the recipe for each block. Like, what should be my abort limit? Okay, I generated a pattern, it is looking good, but I see a several like kind of hotspots in terms of toggle rates, right? That could actually create voltage droop, causing my chip to fail. So now maybe I need to fine tune my recipe for power. So similarly, right? So when engineers spend to improve the coverage, but also balance out some of these other metrics, they kind of fine tune, spend a lot of time refining that. And today, if you see, right, so ATPG today, the way how the pattern is generated is like there are selective care bits, like in a way, like for every pattern, it identifies specific fault sites that it's targeting, and it will try to optimize that fault sites, and rest of the patterns are like randomly filled. Now, what happens is, so eventually it could lead to a lot of overlapping or redundant patterns. Now that is something we could avoid to kind of improve the efficiency of the patterns that we had, because this will directly contribute to the number of patterns that I'm going to generate. And the other one is like as the design gets complex, now it's not like you can take this recipe and apply it directly, right? Like we need to analyze the design further. Okay, why is my coverage not going up? Maybe what is a hotspot? Do I need to do a test point? And we need a lot of this analysis as well. So it's not scalable today in a way when the design size scales up. And the other one is like the traditional fault model that most of the companies they do is like stucket and transition fault models. And so there are companies who also do advanced model like the cell aware and power aware ATPG. But so if you see, right, just to give an example, if let's say if my transition delay fault testing is taking 2 days to finish. Now, in some cases, we have seen cell-aware transition delay could go for can run for a month or more than that. So it's like it's the volume of data that it does, or the way how it's like the number of patterns that it generates. It's kind of not directly scalable in a way. Now, so taking these gaps, now can we look at these gaps that we see in traditional ATPG, and then can we use AI into it? So that's where, like, if you map now taking the same things, right? Okay, so if I go ahead and then do a manual tuning, can ATPG help me there, right? So that's where the automated optimization that AI brings in will help. So we can create ML models, right? And then what it can do is it can look at the previous designs, the pattern generated, and it can try to generate the pattern and see it can see for various configurations how the pattern was generated. So it will try to maybe come up with some kind of permutons which will see like, okay, this is a combinatorial heavy design, and maybe for this design, this kind of recipe is working. So it tries to look for the patterns, which is actually helping, right? Now that's where like, so if you feed a lot of this historical data to it, your like ML models, it can take this kind of kind of go chunk over it, and then kind of crunch over it, and then come back and say that, okay, hey, why don't you go ahead and then use these settings? So now that manual thing where engineers are spending hours and hours of time to kind of come up fine tune the recipe is now kind of taken care by the ML model, right? And then the same thing, right? So we were looking at redundant patterns in the traditional ATPG. Now the question here is like, can AI now look at the patterns that were generated and then see if it can fine tune the next set of patterns that it generates using some kind of unsupervised kind of learning models that are there, and then see if it can further optimize it, right? So that's where we're relying on AI to do it. I mean, if you take it, right, I mean, there are different AI models, like there are like supervised learning, unsupervised learning, and there are like reinforced learning and deep learning, right? So there are like different types of AI that are there. And so supervised learnings are where we feed the data, like we label them, hey, for this setting, for this thing, this is the one that's happening. But if you look at unsupervised learning, so what it does is like it tool tries to come up with its own like analysis, looking for hidden patterns that we tend to miss out essentially. So that's where this unsupervised learning is going to help and see if it can improve further the pattern generation there, right? And so the third point that we discussed in the traditional ATPG is the scalability issue. So here, now what we are looking at is we are looking at the ML models to kind of look at every block hierarchically and then see if it can fine tune the recipes on its own, right? So it kind of can do an adaptive learning on its own. And same thing, right? I mean, instead of using statistical fault models, now maybe with the same whatever the unsupervised learning that we have or reinforced learning that we can do, can engines now identify like, okay, what kind of faults are prone to a particular net, and maybe go ahead and then target them, and then maybe see if it can recover it essentially, right? So that's how today like the AI is kind of helping us in kind of look at some of these traditional limitations and then help us mitigate them. Now, okay, so what is the industry solution that is out there for this? I mean, today, if you see, so Synopsys has this TSO.ai, test-based optimization. So where basically you can think of it like so it can help in coming up with a decision on, okay, what should be my compression ratio is going to look like, okay, how many scan-ins that I need and how many compressed outputs that I need to achieve a better coverage. Now if I go through it and then also enable my machine learning to fine tune the recipes, so what we have seen in general is on an average uh, between a traditional run, which is engineer driven or existing run, versus a fully AI driven run. So there is like almost like on an average 20% test time reduction. That we see. Basically, it's going to come up with a good recipe for your scan in, scan out, and it's going to identify how many chains are needed, and then that's how we are calculating the test cycles as well. Right. So this is like, I mean, so there is already a like this like published paper. So I put the source here. Uh, and when you get the presentation, I think you can go over them in detail, essentially. So basically, the idea here is, can tool look at the design, fine tune my input parameters, like what's going to be my codec size, everything, and then fine tune my ADPG recipe, and then go ahead and then fire parallel runs to do some kind of initial set of learning, and then use that for the next set of runs so that it can automatically come up with the recipes on its own. Okay. So the next one that we have is basically the AI assisted scan diagnosis and yield optimization, right? So so this is an interesting one, right? So now that we have generated a pattern and now we are feeding it to the actual chip that is out there for testing. Now there are like some failures that are happening, right? I mean, can I draw some conclusion out of it, right? When today, if you see, I send a pattern set. See, what usually happens in a design life cycle is we have a chip, we generate the pattern set, and now this pattern set is loaded onto the ATE when the chip comes back. Now you run, it passes, good, not a problem. Now when it fails, so that's where the real kind of work starts. Now when it fails, how do you correlate a particular given pattern to which logical net or a cell is causing it, or which physical defect is causing it? Is that path having some timing issue? Is it because it sees some slowness in the chip, right? So there are several factors that it triggers. Now usually that's very I would say like time consuming and manual in a way to map these real-time test failures into what could have actually happened. So you're going to differentiate between, is it a manufacturing fault, or is it my setup issue, or is it because the path was critical and it's failing for that particular scenario? I mean, how do we classify between a like input pattern generation issue versus a real issue versus like some anomaly that's there in the design, right? So that's where um, the traditional ones is like a lot more time consuming, and AI is gonna kind of help look at some patterns there and see how it can help us, right? I mean, today, if you see, whenever there is a failure that happens, right? So we rely on some rule-based heuristics to classify them. I mean, when I say like rule-based heuristics, right? So, I mean, these are like what it does is like, I mean, today in a normal flow, whenever there are failures, we try to group them physically, and then we see, okay, are they physically located in a single place? Okay, now is it because there are some interconnect faults or some bridge faults or shorts or what's happening? So that's one, right? And then, or there could be a temporal clustering that we do. Temporal clustering is like, maybe what happens is we keep running these and then we see that the failures recur over a period of time. Now, then we know that if the failures are recurring over a time, it's not random in nature. So it could be a process induced, or it could be some recurrent functionality that is triggering it, right? So that's how this temporal clustering is going to help. Or, and the other one is like we can do a signature based testing. Like we can see like, okay, these are the failing patterns. Now I compare them with existing known models. Okay, I know that like this kind of model means it's a stuck at fault, or maybe this kind of model is maybe my transition like transition delay testing issue, right? So we try to compare the signature mapping. So that's how today we do. So it's very time consuming. And the other one is like it's always a reactive post-silicon debug, right? Like what happens is like once you get a failure, you go back and then you open your database and you see, okay, how is my timing looking like? Is it congested? I mean, do I have enough margin? And all these kind of analysis happens today. And then the problem is, unfortunately, since it's manual in nature, we go through this for one chip. When the next chip comes, again, we'll go through it in a manual way. I mean, it's mostly a tribal knowledge that passed on from the engineers that have been working on multiple generations of product, right? I mean, it's not something that is automated fully in a way. And then the other thing is like when you have these failures in the like when you get your diagnosis log, right? Now, how do you differentiate between a random failure versus a predictable failure? Right? I mean, that's where a lot of this heuristic-based segregation and everything happens. And even after that, we might just get like some of these noises can how do I say like corrupt our understanding of what could be a systematic problem that is there, right? Now, taking these traditional gaps, now how is AI helping us in addressing these gaps that are there in the traditional diagnosis flow, right? So the manual work is now changed into an AI-driven classifier, right? So what it can do is it you can feed in all kind of historical data that you have, the failure signatures, your past post-silicon failures, your layout information, pattern information, what kind of failures you have, and all the categorizations, right? Now that what machine is gonna do is like it's gonna take and then run through it, and then it will be able to get identify the patterns to help you. Okay, what kind of issues are we now running into, right? So that's what exactly is going to happen now. And the other thing that we are talking about is the reactive post-silicon thing, right? Now, one of the things that we can do now with the AI is like, I mean, don't wait for the silicon to be back. Maybe what you can look at is like, we can see if there is an opportunity to look at my layout, look at my metadata, like how is my lithography simulations looking like, or how is my functional simulations looking like, what is my timing looking like, and then I'll feed my past silicon failure issues, right? Now, can I use this information to identify what are all the potential fault sites that can happen? And then is there anything that I can do to refine my analysis further around it? I think that's where the machine learning is going to help, actually, right? And the third one is that we talked about in the traditional approach is the inability to learn because everything is manual, right? But here, since a lot of this learning that the model is doing, it's stored, and you can actually leverage that to kind of go ahead and then clean up all your setup issues and then make sure that you're targeting the real issues, right? And then what we have seen is like we see about the setup time reduced by almost 40% because we have this adaptive and additive learning that these models can do, right? And the last item that we had in the limitation was a noise, right? So, but now where AI can help us is like it can actually do some kind of a root cause deconvolution. I mean, what it's gonna do is like it's gonna go and try and look at the patterns and then see, okay, how many of these are following a specific patterns and how many of these are purely random in nature. Like it's gonna actually help in separating out these from the logs, and then it can now you can actually focus on like the actual failure analysis that is happening. Now the place where this helps is if I can get this correlation, what I can also do is maybe for a particular process, if my standard cells are behaving, let's say, overly pessimistic, maybe I can go back and change my library cell modeling in such a way that I can capture that in the design phase itself, right? So that's where all of this information is gonna actually help us in a way. So now, if I look at the industry solution that is available right now, if I take a look at that one, right? So what we have is like, so Siemens has this like kind of root cause deconvolution approach. So what Siemens doesn't does is like it cannot take your layout information, your left def information, you put it your kind of diagnostic log that you get. Now what it's going to do is it's going to go through your layout information and it's going to look at your historical failures, and then I need to look at your current existing diagnosis report and then see, okay, is there any suspect list that it can produce where I know that, okay, these are the ones that are actually causing, and this could be maybe maybe an input issue, or it could be because there is a manufacturing fault and whatnot, right? And then, so the key here is like basically it kind of applies that algorithm to remove any noise and then predictably come up with like what is your yield limiter, and do I need to kind of maybe decongest a particular design, right? Or maybe do I need to play around my clock frequency, right? So that kind of information we'll be able to get it. And similarly, like yeah, so what it's helping us is like you can take this information and you can actually improve the failure analysis, like as I told earlier, right? I mean, you can use this to maybe improve your library cell modeling, or maybe you can improve this to fine tune your cell level model for the pattern generation, right? So that's where this diagnosis is gonna help, right? So the key factor here that we are achieving is like we have a faster turnaround, and since the noise is eliminated, we also have a cleaner defect Pareto here that can actually, this information we can feed it back to the manufacturing team, and they can look at to see, okay, what needs to be fine tuned from a process standpoint. Okay. And so the next, like some common practical issue that we see is my ATPG creating like voltage droops or failures in the silicon, right? So can I rely on AI to flag any IR sensitive, basically my the current and resistance here, right? The voltage, like wherever we see the voltage droop, can I flag those high dissipating area, predict them so that I don't run them on the chip, right? So if you see ATPG in general today, right, is whenever you do a shift, it's a toggle intense activity because let's say I have million flops in my design, and if I'm shifting data through the flops, what I'm looking at is like all the million flops toggling at the same time. I mean, so it is gonna actually burn a lot of power and then pull the like increase the load on your power network, right? I mean, this is, think of it like, I mean, a classic a real world example and that we run into is like, okay, we go turn on all the appliances in the house, right? What ends up happening is like we end up getting these power fluctuations, right? A similar thing kind of happens in the chip as well. So you have your supply rail. Now you have all these flops toggling at the same time. So that creates a voltage droop, a drop in the voltage on the silicon, or like it could create like hotspots that could even damage your design. So instead of testing, we might end up damaging the design, right? So we should avoid that. Like, so one of the key things is it's not just the coverage, but how do we avoid such things, right? So that's one of the interesting areas actually. Now, just to give a real-time example from one of the designs that I was working in the past is like we had a path which was very good and which had a good 150 PS positive margin, right? But we went to silicon and then we saw like, okay, the pattern is failing there. So we never suspected that a passing path could actually fail. But then after a lot of debug from timing and getting some like overall plots from like the manufacturing team and from the post-silicon team. So what we found out was that there was a heavy toggle activity happening around that region, and we had to actually and that voltage, that toggle activity actually made a path that was passing by 150 PS margin to actually fail now. So that's the level of impact we are talking about. So that's why this IR sensitivity is really important these days when we generate the pattern. Okay, so now same thing, right? So when I look at the current traditional way of IR aware pattern generation that I do, right? So the bigger drawback is like today when we do ATPG, we are only focusing on fault models, what kind of design. So we are completely ignoring what's my power grid behavior, how is my power network distributed, is this fault closer to my power, or is it fault faster, like farther away from my actual source of the power network, and lot of these things, right? And then how is my peak current for this pattern? Right? A lot of this data, it's not directly fed in. And now other thing is like patterns today, like it's primarily targeted for fault coverage, right? But when you take that approach, it's gonna create this large switching activity, the simultaneous switching activity, the SSO event that I mentioned, right? And today people do some IR analysis to see if there are hotspots of the pattern generated, but that pattern actually happens after the patterns are generated and we do, right? I mean, that's it's a little bit like a two, now it becomes a two-step process. Like you generate, you find issues, and you go refine, right? And then maybe when you refine, you figured out that okay, you came up with a power recipe, applied for all the block, and all of a sudden start seeing that for some blocks the patterns start bloating. So that's not like is also not going to help us directly in a way. And again, right? So when since we are relying on a manual work, there is no historical data that we're relying on to predictably identify, okay, what are the like high risk patterns that we need to avoid. Okay. So now taking these gaps, now looking into how AI is actually going to help us in like in bridging some of these, right? So now it's not a static model anymore, right? So what AI actually does is like we can use the ML models to kind of do a surrogate modeling of the power network. So it's not like a real modeling, but what we are looking at is like a lightweight neural network kind of to give like a to do some kind of an IR simulation on how the patterns is going to look, because we don't, for every pattern we don't want to do like a full IR analysis, right? That's very time consuming. So what we do is like, okay, we do generate the pattern, and then can we get a quick feedback to see how this pattern is looking like and what is the voltage drop impact? And then can I just see either it's a like kind of a go or no go pattern, right? So this how this modeling is helping us actually. So this lightweight neural network, IR drop analysis is helping us, right? And now you're predictably modeling with the switching activity information. So, which is good, right? So because now then the patterns now are sensitive to your SSO intensity, like how much activity, switching activity am I expecting on this one, right? And other thing is like what you can also do is basically you can take the patterns. Maybe once by your prediction you identify that okay, these models, like maybe some patterns I see, like I don't see a clear go no go kind of a decision, or I see that okay, there is a severe impact of this pattern, right? What we can do is then maybe we can take this limited set of patterns and do an actual full IR simulation to see how much correlation are we getting from this lightweight model to this, right? So that can further refine your pattern generation. So in a way, if you see, right, like we can rely on the ML model to do a pattern ranking, like high risk patterns, medium risk, low risk, kind of go no go, and then we can take an informed decision. The tool can take an informed decision on the fly whether it needs to kind of take this or reject this. Now you can take this one step ahead, and then you can even introduce like your layout information to this. Maybe what it can also do now is like maybe it can also try and understand what kind of layout is causing these kind of toggling activities as well, right? So that information can also be auto extracted by the AI tool today. Right now, looking at this, are there any existing industry solutions that are helping us here? Yes, definitely, right? I mean, if you look at the Synopsys test space optimization, so it can be integrated with IR drop analysis tool like Prime Power to guide ADPG towards like a power safe pattern. So you can actually generate a like you can include your power targets, like what kind of toggle activity that you want to achieve, give a target to it, and then like tool should be able to get this, like you're going to feed in your like kind of VCD information, your toggle activities, right? And then tool can actually generate the patterns now, which are which are toggle sensitive patterns. So similarly, Siemens Tessent has few extensions, right? So where they have ML models to kind of similarly predict this IR hotspots. So they kind of work with Caliber and Power Grid simulation to kind of correlate this scan activity with layout induced uh, like IR stress that is there. So like yeah, so if as you can see, right? I mean today AI is pretty much it's not in the theoretical space in the real time, like in the real world, right? In the industry as of now today. So like these are some of the like kind of like high burning like kind of problems, and then like there is already like solutions out there which is actually helping us to learn with the historical data, identify the patterns, and then it is actually helping us improve the overall efficiency in a way. Okay. Now, one of the things, right, before I go into the next slide, right? So today, if you see, there is also a concept of digital twins. So the idea here is like as you go through your real-time design, you actually build a digital model of your full design. So you start feeding it microarchitecture, you start feeding it your historical data on how the overall design, the PPA was, and then and your process information. Now, as you run through, you also feed the same like based on this your actual run. Okay, what is the timing looking like? What is the performance looking like? You go keep feeding into this model, a virtual model, and this virtual model so the expectation is that like let's say if it can mimic your real-time design even before the manufacturing happens, think of it like the advantages you have. So you have a model which is closely mimicking what it's gonna look like when it's actually manufactured. Now that is gonna open up a lot of pathways for you, right? I mean, now what it can also mean is I can actually generate the patterns with all these things. I can virtually simulate the patterns, and then I can see them how it's gonna get impacted, right? I mean, think of it that way, right? I mean, you're actually trying to simulate something that doesn't exist and then see if you're close enough to the simulation, right? I mean, if you see this kind of a virtual simulation, it's a similar concept, right? I mean, if you look at like any of this car crash tests that happens, right? I don't think like let's say high-end cars like the BMW or like kind of we kind of go to Rolls Royce or whatnot, right? So we don't expect them to do a crash test 100 times because that's going to burn a lot of money for them, right? So they are also laying on some kind of simulations to fine tune and then limit the actual physical crashes that they do, right? The concept is very similar, right? The digital twin concept is very similar. Like, can I build a model and keep on improving it such way it mimics my real world chip when it's get manufactured? Then I can actually use that platform to feed in that, right? I mean, that's one of the areas that you can see, like, I mean, there are some research papers that are there that will actually help, like, kind of, um, like, like mimic how the patterns would look like, and then maybe refine your patterns even before the silicon comes, right? So having said that, I mean, if you look at it, okay, what's there now? Okay, we talked about the existing solutions. We talked about like a digital twin kind of a thing, right? So what's there, right? I mean, today, if you see, um, what eventually where we want to get to is like we want ATPG engines to be able to continuously learn, and we keep giving it real-time feedback, and it should be autonomously able to refine the test strategies when it comes to the next design, right? I mean, starting when I get the microarchitecture and then my initial design, it should be able to come up with my test strategies and how I want to like test my design and how it's gonna compression and everything gonna distribute, scan network gonna be distributed, and how it's gonna be my pattern generations and stuff like that, right? And then the other thing is like we need we so as the design complexity increases, right? So everything is close knitted. So it's no longer like individual domain that they work in their own silos verticals, right? So every domain need to collaborate now. Like for example, I build a design, I do a scan stitching. Now I go to physical design. So my physical design engineer complains, hey, I see my congestion going up because of your scan net. Can you optimize your codec? Can you not just put them one big codec in for the design? Can you split and put like one in the left side of the design and another in the right side of the design, right? So can you optimize it? So can these decision be made automatically by the tool, right? And can I use my previous diagnosis data to see identify maybe the hotspots and then do some stress testing, right? I mean these are the kind of cross domain we are looking at, right? So we're looking at power, physical design, DFT, and like timing and everything, right? And not just that, like now depending upon my kind of manufacturing or packaging that I have, like am I doing a 3D IC or a chiplet? Now what should be my fault model look like, and can my ATPG fine tune automatically based on what kind of packaging that I run into, right? And the key part here for everything is like um, can I take the real time data, process it, and then be able to get something meaningful out of it or not, right? I mean, that's the key part here. And I mean, like the last two ones, if you see, right? Think of it like today, if you see, we generate the pattern, we optimize the pattern, and then we feed it to the ATE, the automatic test equipment, right, to do the testing. Now, I mean, one thing that we can look out for is like, hey, you're doing a testing, you found something. Can you adaptively kind of regenerate the patterns, and the test patterns be kind of deployed on the fly, right? I mean, that way, it's like you don't need to spend time again regenerating the patterns, right? I mean, that's something very like the futuristic that we're looking at. And then the same thing is looking at my historical data, what I want to, the place where like people are trying to reach to, it's like can it come up with the compression schemes and architectures and like and then my pattern settings and everything on the fly, right? I mean, this is like completely autonomous kind of a decision. But yeah, I mean, today if you see there are drawbacks because at the end of the day, the model is only as good as the data that you feed it in. So it needs a lot of fine tuning and as I mentioned, right? I mean, like AI tools are not logical, right? So they look for pattern and everything. So it still needs manual intervention and optimizing the stuff, right? But it will definitely help ease in cutting down the time that we spend on some of this decision making, complex decision making like steps that we have in between, right? And so kind of key takeaway or the summary of the entire presentation, right? I mean, so if you look at it like we are not looking at AI as just as an enhancement, right? So now what we are looking at is like it's a paradigm shift, not just in DFT, right? For the end, like in many places today on how a particular technology is actually from the stage where it's actually conceived to the stage where it's actually deployed, and then like can I auto refine it to kind of make some adjustments and evolve it or take it to a next level, right? So that's where the AI is actually helping us today. I mean, like blocking the holes where it's manual intensive effort, or some of the patterns that are too subtle for us to recognize, or some of the permutants that for us too complex for us to kind of uh, kind of on the fly track, right? And definitely it is, I mean, I kind of provided a comparative analysis between the traditional and the AI-based approach. I mean, you can clearly see that it's actually helping with a lot of traditional bottlenecks that we have, right? So the ML is actually helping us in those bottlenecks as well. And it's no longer a theory that we are talking about, right? So there are production grade tools from major EDA vendors that people have adapters, and these early adopters also have seen a good amount of gain in the coverage cost, right? I mean, there is a heavy like kind of research happening on what are the some of the other like key areas where we can improve, but already we do have solutions in place for the common problems that are there, right? And I mean, definitely, right? So I mean, what we are looking at is like we want a predictive way of generating, like doing my design for test to make sure that my time to market, the test time is coming down, and it's helping kind of to catch up with the competitive time to market that we have. And also it's to ensure that like the number of DPPM or the defective parts that are found on the field are gonna reduce, right? So that's where we are hoping AI to help us eventually. Yeah. So yeah, I mean that's what I had. So hopefully you got some insights into what's happening in the industry and how AI is actually helping addressing some of these challenges that the traditional flows have. And definitely, I would say at this point, it's augmenting. It's not replacing uh, from where the current state it is, right? It's definitely augmenting and improving the efficiency of every product company that is out there. So at least that's my take. So I'll open the floor for the questions.
Okay, dear participants, if you have any questions, you can ask.
So hopefully, I mean, I didn't go too fast, or so like I believe like you were able to catch up with the topic that I was trying to cover.
Yes, sir, it was okay.
Not good, just
Excuse
okay.
me, sir.
Sorry, go ahead, please.
I'm Umman Taragan. I'm from Mar Basilius College in Kerala,
Yes, yes, sir. Please go ahead.
and
Yes,
I was earlier at ISRO, Trivandrum.
sure.
My question is for a processor which we buy from Intel or for AMD, whether we can have the test patterns generated using the AI, where only the pinouts only will be available, no, and only the instruction sets, but no more, no details with respect to the inside gates or multiplexes or other macros. With the available information, whether we will be able, whether AI will be able to generate the test patterns to cover the maximum fault coverage.
Okay, so today, if you see, let's say if you just have the pinout access information, right? So the capability that we have today is like we would be able to come up with what is the best test architecture, what kind of compression technology do you have, and once you implement it, what we can also do is like the pattern generation tool can you feed the netlist information for it for the existing
No, we
processor that
don't
you have.
have, sir, we don't have the netlist information. It's like a black box. Suppose we are buying that 80960 MC processor from the Intel
Hmm,
or
hmm.
another pipeline architecture from the Intel. That's all. We are limited with a product only, with no accessibility to the internal points.
So that might be tough. So because today, if you see, right, every company they don't want people to do a reverse engineering. So some of the
Correct. Why
test,
I'm asking that because ours is for high reliability missions. No,
right, right,
that's
right,
why. So we cannot afford to any failure is not an option for us.
correct.
Although a lot of tests might have been done with respect to design validation by the company, etc., still we would like to have the full to have the confidence on us.
Got it. Got it. I think today, I don't think traditional test is gonna help, right? So, I mean, if you just have a working model, I mean, most likely it's like any of the vendor testing or validation that happens. I mean, we are limited with what kind of functional simulation models that we can do. But I don't think
Because we have an experience with the Copaint microcontroller, where
Mhm.
some instruction was in problem, which we detected through our own this simulation based test.
Correct,
So
correct. I
that
think
is why,
today,
although it will not be having that much impact, we found some instruction issues. So similarly, it might have gone through many areas of testing and validation. So somehow something, if it is not caught at their side, which we should not miss because it is a high reliability missions, no? That's
Yeah,
quite
got it. Good. I understand the point. I think today the only way to achieve that is you're using your functional simulation only. Unfortunately, the traditional
Mm.
test is not going to help us there because we are limited with what kind of exposure.
Correct. But in that case, whether this AI will be able to generate the patterns for which what should be the input?
Got it. I might have to look into that, sir, because
Okay,
I
okay.
haven't explored
No,
much on the functional simulation side, but I'm pretty
no
sure
problem.
there
No
could be
problem.
some ongoing efforts there. But what I can at least say is that like your traditional test patterns, right, will not help,
Yeah,
unfortunately. Yeah, it's
yeah,
mostly,
that's fine.
as you
So,
mentioned, it's based on the functional simulation.
or we should have some model to be generated, and based on that models, we should have the fault models and then generate the test vectors for it. Is it not?
Correct. Or the whomever you have you are getting the chips, right? So if there is a way for an, I mean, so one of the latest advancements that are happening, right? So instead of using your ATE, so there are already IPs that are being built where you can use your USBs to actually send the patterns and then look at the output. Now, let's say if some of the upcoming chips, if they can provide your test access through some of those common general purpose IOs, right? Like if PCIe's or USB, if that is enabled, then at least at a system level, you will be able to feed the patterns, and if the configuration supports, you will be able to do that. But that depends on the actual chip developers adapting some of those like general purpose access based test. Otherwise, it's just the functional simulation that you're limited to.
Okay, sir. Thank you. Nice of you, sir.
Thank you. Yeah.
Pradeep sir, good evening, sir. Small doubt. Sir, for college students, we need any free tools are available, sir, PD related.
So physical design related, I need to check, sir, but at least what I know is like a while back I was looking at ABC, at least the synthesis tool, there was one from the Berkeley University that I'm aware of. But for the back end, I need to check, sir. Yeah. But I know synthesis back in the day,
Why?
we
Because
were.
actually we are
Mhm,
license we are getting, sir. We are getting 180 nanometer per cadence in
mhm,
TPL technology we are getting.
mhm.
That is a limited only. We are not having FinFET technology. Only CMOS only we are having, sir. But we are having the knowledge of only schematic. This only, sir. Up to synthesizing we are doing. When one counter program alone, we are doing GDS2 files, sir. We are not
Got.
doing that much also. We need
I
some
can
at least
definitely check.
28 nanometer we are using it at least benefit for students also, sir.
Got it.
Anything is there, you can post in
Mhm.
our group, sir.
Sure, sure. I can check that. Like one thing that I know is like definitely some of those major EDA vendors, they do have college programs and university programs tie up. So I know that
Yes, sir.
Synopsys has one tie up with IIT Hyderabad. Sorry, IIT Tirupati, if
Okay.
I'm not mistaken, not IIT Hyderabad. Sorry, IIT Tirupati. There should be some tie up from a university program. So usually the
Okay, sir.
licensing and everything is through that hub there. So I can check,
Yes.
sir. I mean, at
Our
least if there
college
is
also
anything.
we are in college Bangalore, sir. We are also having
Got
cadence
it.
only, sir. That is also 180 nanometer. NTPL university bundle they are giving 3 years, sir. But they are not having all the features. Only limited only we are having, sir.
Yeah,
And
yeah,
their
I
full
think
chip we are not doing. Just up to placement and routing stage we are doing, sir.
got it. Yeah, yeah, I might have
Thank you,
to
sir.
check,
Thank
sir,
you
for
for
the
your
previous
lecture. It's
error.
very useful for us, sir. Thank you,
Thank you.
sir. We can
Thank you.
share to this knowledge to our students also. Thank you for
Thank you.
organizing committee, all the people, sir.
Thank you.
Thank you.
Yeah. So any other questions?
Then anybody else who want to get your questions clarified, you can ask. Okay, thank you so much, Mr. Pradeep Bharadwaj. It's a nice presentation from you. And
Oh, thank.
our participants has gained knowledge from your presentation, and this will help all the participants. Thank you so much for your nice, beautiful presentation. Thank you so much, sir.
Thanks, sir. I think thanks a lot for all the participants as well. I think so. Hopefully, it was informative. At least I wanted to give an exposure to what's happening. I mean, definitely there is a lot of detailed work happening, and every vertical is its own. I mean, you can think of it, right? I mean, I spent like 14 years just on the scan implementation, and I still feel that there is like a lot of things to explore around it. So, I mean, so VLSI it's like a pretty huge universe on its own. Like every vertical has its own like advancements happening. Yeah, if there are any questions offline as well, also please feel free to reach out to me. I'm available on LinkedIn, and we can connect over LinkedIn. And if there are any queries, if there is any generic thing that I could help us, I would be definitely happy to help. Thanks, everyone.
Thank you. Thank you so much, sir.
Thank you, sir. Thank you, Nagendra, sir. Thank you, Pradeep, sir. Thank you, all the participants.
And I request all the participants, please give feedback. The feedback link is shared in WhatsApp. So you please give your feedback. And you can leave the session. Thank you.
Thanks, everyone. Bye.
Pradeep, thank you. You can leave, Mr. Pradeep.